Drop a piece of solid metal into a strong acid and a violent reaction kicks off immediately. But what is physically happening down at the atomic level? To find out, we are going to run a classic baseline experiment. Our starting ingredients are solid zinc granules and a solution of dilute sulfuric acid. To safely contain this reaction and actually measure the output, we need a specific lab setup. We'll place the zinc and acid in a sealed test tube and attach a delivery tube that feeds directly into a secondary beaker filled with a simple soap solution. This sealed environment ensures nothing escapes unnoticed. Once the reaction begins, we can track exactly where every single atom of our starting ingredients ends up. The moment the sulfuric acid hits the zinc granules, you will see a rapid formation of gas bubbles erupting directly on the surface of the metal. But we have an immediate problem. The gas being produced is completely invisible and odorless. If this tube were open to the air, the gas would mix into the atmosphere and be impossible to track. That is exactly why we use the soap solution. The soap is not a chemical reactant here. It acts as a mechanical trap. As the invisible gas travels down the delivery tube and escapes underwater, it gets encased in a thin film of soap. By packaging this elusive gas into temporary floating bubbles, we now have isolated pockets of our mystery product ready to be tested. To identify what is inside those bubbles, we apply a standard diagnostic test. We take a burning candle and bring it close to one of the floating bubbles. It immediately ignites with a bright micro-explosion. You will hear a distinct, sharp pop sound. That specific auditory signature tells us exactly what we are dealing with. Hydrogen gas is highly combustible, and it burns with that characteristic pop. Knowing that hydrogen gas is our output lets us solve the rest of the chemical puzzle. Let's look at this equation. We started with zinc and sulfuric acid on the left side, and we know hydrogen gas, H2, escaped on the right. Take a moment and pause the video here. Based on the atoms we started with, try to deduce the chemical formula for the compound that goes in the blank space. The zinc metal physically displaces the hydrogen atoms from the acid. Those hydrogen atoms pair up and float away as gas, leaving the zinc to bond directly with the remaining sulfate, forming zinc sulfate. Whenever a metal physically displaces hydrogen atoms from an acid like this, the newly formed compound left behind in the solution is classified chemically as a salt. This displacement behavior is not unique to zinc and sulfuric acid. You'll observe this exact same reaction profile across most reactive metals when mixed with strong acids. Because the underlying mechanics are consistent, we can abstract our specific experiment into a universal word equation. Acid plus metal yields a salt plus hydrogen gas. To master these reactions, remember these three core concepts: the general word equation mapping the inputs and outputs, the candle pop test used to prove the presence of hydrogen, and the rule that the resulting salt is always formed by the metal bonding with the acid's leftover elements. Depending on the starting ingredients you choose, the specific type of salt left sitting in the bottom of your beaker will change, but the rapid evolution of highly combustible, popping hydrogen gas remains the reliable, universal signature of an acid-metal reaction.